Hello everyone, this is the 8th lecture on the real sequences, and in this lecture uh, today we are going to discuss about subsequence of a given sequence. So let's start. Subsequence. Suppose that we have a sequence an. This sequence is given. Sequence is given of real numbers, and here we construct a sequence of natural number. This is actually strictly increasing sequence of natural numbers. Here it is important, we construct a sequence, strictly increasing sequence of natural number. Then the sequence here n is in suffix of a and k is in suffix of n. Then this is called subsequence of given sequence an. Clear? Example: suppose that we have a sequence an where nth term of the sequence is 1 by n, and here we will try to construct different subsequences of given sequence. We can have more than one subsequence for a given sequence. And here we take nk is equal to 2k, okay, and here actually k is 1, 2, 3, 4 and so on. K is a natural number, okay, which is starting from 1, 2, 3 and so on. So the subsequence nk of given sequence is actually here nk, this will be 2, 4, 6. Therefore we have a2, a4, a6 and so on. Actually we have the terms of the given sequence a1, a2, a3, a4. So here we pick only even terms of the sequence a2, a4. Similarly, next term of the given subsequence will be a6, okay, and this is from the given equation 1, 1 by 2, 1 by 3, 1 by 4 and so on. From the given sequence a2 is 1 by 2, a4 is 1 by 4 and a6 is 1 by 6. So this is the subsequence of the given sequence an. In similar way we can construct another subsequence of the given sequence. Here take actually here we take only even terms of the sequence. Similarly, we can take odd terms of the given sequence. If we take n k is 2k minus 1, so this will be actually, we take here k is equal to 1, 2 minus 1 1, k is equal to 2, 4 minus 1 3. We have here odd terms. Here we take k is equal to 1, 2, 3 and so on. Then subsequence a and k, this will be a1, a3, a5 and so on. So here we have odd term of the sequence are odd term of the given sequence 1, 1 by 3, 1 by 5 and so on. And this is also a subsequence of the given sequence. If you want to construct a subsequence, so you just need to construct a sequence strictly increasing sequence of positive numbers. Similarly, if we take nk is equal to k square, so here we take k is equal to 1, so this become 1, k is equal to 2, we have 4, k is equal to 3, 9, k is equal to 4, 16 and so on. Then subsequence a and k, here we have a1, a4, a9, a16 and so on. This is also a subsequence of the given sequence 1 by 4, 1 by 9, 1 by 6. These terms comes from the mother sequence, and mother sequence is here actually an is 1 by n. So it is clear that for a given sequence we can construct infinite number of the subsequence. Actually, next we note some important result regarding subsequences of for a given sequence. Result number 1, if a sequence an is convergent, convergent means it has a limit with limit L. Then every subsequence of an is also convergent with limit L. Result number 2, if all subsequences of a given sequence, or we can write of a sequence, if all sequences of a given sequence are convergent, then it is not necessary that the given sequence is convergent. Result number 2 says that if we have different subsequence of a given sequence, and suppose these all subsequences are convergent, so it doesn't imply that the given sequence is convergent. For example, we take a sequence where nth term is -1 to the power n. So here actually, if we take a sequence of even terms of given sequence, then we have 1 1 1 and so on, because we know that the even terms of the sequences, here actually the mother sequence is -1 1 -1 1 -1 and so on. Okay, so this is actually constant sequence. If a given sequence has only one real number, means all terms are same of the given sequence, then this sequence is called convergent, and this sequence is called constant sequence, and we know that constant sequence is always convergent. Okay, so here 2k goes to 1 as k tending to infinity. Here we are taking k tending to infinity because here we take subsequence nk in terms of k. Clear? And or if we take subsequence, then the all terms of this sequence are -1 -1 and so on. So it is clear that here also this subsequence converges to -1 as k tending to infinity. So here it is clear that two subsequences of the given sequence a 2k and a 2k minus 1, these two subsequences of the given sequence are convergent. One converges to 1 and other converges to -1. Okay, but the sequence an is not convergent. Actually, for a limit point of a sequence, we construct a subsequence. Okay, so we can write for a limit point of a sequence an. There exists a limit point L of sequence an, and there exists a subsequence suppose a n k of given sequence an, such that this subsequence convergent and converges to L as k tending to infinity. Similarly, if we have two limit points, then we can construct two subsequence, and these two subsequence converges to that limit point. Okay. In result 1, actually we write if a sequence is convergent, then all subsequence also convergent and converges to the limit of the mother sequence. In result 2, we write if the subsequences of a given sequence are convergent, but the mother sequence may not be convergent. Okay. So under what condition sequence is convergent? If all subsequence are convergent. So we write this in result 4. If all subsequences of a sequence are convergent, all subsequents are convergent, and these all subsequences converges to same real number L. All the subsequents are convergent and converges to real number L. And suppose this sequence is an, then an is also convergent and converges to same real number L. Okay. So here it is clear that if all subsequences in node 2 we actually construct two subsequences which converges to different real number 1 and minus 1. If we construct all subsequences and we see that all sequence subsequence are convergent, then this implies that mother sequence is also convergent and converges to the same limit of the subsequences. Clear? So for the in the terms of subsequences, we can write Welian-Weierstrass theorem as actually we write here for a limit point there have a subsequence. So we can say that if a sequence is bounded, then it always has at least one convergent subsequence. Result 5. Actually, Welian-Weierstrass theorem for sequence. We say that this theorem says that every bounded sequence has at least one limit point. Or in terms of subsequence, every bounded sequence has at least one convergent subsequence. Actually, sequence is bounded, then it has a limit point, and we can always construct a subsequence for the given limit point which converges to that limit point. Okay, so these are the equivalent statement. Okay, some other use like Robert G. Bartlett use this statement of the Welian-Weierstrass theorem. Now next topic is complementary subsequence, and the complementary subsequence we will discuss in the next lecture. Okay, thank you.